Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
All right, so welcome to the Back to Basics track, and welcome to the second part of designing classes. So if you have not been a part of the first part, then again, allow me to introduce myself. My name is Klaus Iglberger, and I'm perfectly okay if you stick to the first name. So I'm Klaus, and I do C++ trainings / consulting for a living. That's indeed my job. And this is now where the experience comes from. The experience about how to design classes. In the first part, I've primarily talked about design guidelines. And the most important takeaways are design for easy change, design for easy extension, and design for testability. That is now the three guidelines, design guidelines we will put to test. This is exactly what I want to talk about again. But now, in the form of implementation guidelines, class mechanics, language rules, things that are just important to keep in mind for virtually every class that you implement. So part 2 is pretty much focused on that purpose. So let's start right away with the first implementation guideline. And the first thing I would like to talk about is data member initialization. So I start with an example, pretty much a question. Again, I have a struct widget. And again, widget is just a name that I made up, or that is usually used to say, well, there is a class, there's something. And this widget has 3 data members: an int, a string, and a pointer to an int. In the main function, I'll now create a widget W. And now I'm interested in what exactly will be the initial value of these 3 data members. So what will be the initial value of I, the initial value of S, and the initial value of PI, the pointer? So think about this for a couple of seconds. Trust your gut feeling, perhaps. And so perhaps you're thinking, the I is initialized? No, it's not. I is completely uninitialized. Perhaps it feels like it's 0, but no, you cannot trust that, it's uninitialized. The string, on the other hand, is probably initialized to an empty string. That is something you can count on. But again, the pointer is uninitialized. And that, of course, is a problem. That, of course, is something that you want to avoid, because it's super difficult later to distinguish an uninitialized pointer at some random address from a really properly initialized pointer, a real and a valid address. That should not happen. Now, there's something very simple that we can do in this situation. I now use, okay, first the rule, true. So what is happening? The compiler generates the default constructor, the one that I'm calling right now, does not initialize, only initializes the data members of class or user-defined type, but it does not initialize the data members of fundamental type. It just doesn't. So here's what we do. We use an empty set of braces at this point. We don't use default initialization, but something that we call value initialization. That's, by the way, something old. The syntax is new, but value initialization came in C++ 03. Now, by just doing that, by just adding these little braces, suddenly, magically, all of these data members are properly initialized. So the integer is 0, the string still is an empty string. That was okay before that. And a pointer is null pointer. Perfect. That is what you want to have. That is great. So as a first side remark, remember value initialization. In this situation, it actually works very, very well. If the class doesn't have any user-defined default constructor, so if there's none, then value initialization, first of all, 0 initializes the entire object. So the int and the PI definitely benefit from that. And afterwards, of course, all non-trivial data members, in this case, the string, are initialized by their own default constructor, which doesn't change it. It's still an empty string, but the I and the PI definitely benefit from that. However, even the best syntax, even this value initialization fails if, guideline first, prefer to create default objects by means of an empty set of braces. Value initialization. It really helps. It's great. But in a nicest syntax fails if you take the responsibility for this function into your own hands. So you're now adding this default constructor. Now the constructor with no arguments, and you don't do anything. Now, despite the fact that we use value initialization, suddenly the integer is again uninitialized, string is still initialized, and the pointer is again uninitialized. Very unfortunate, but kind of expected. You have now taken the responsibility to write that default constructor yourself, but they don't do anything. And the default of this default constructor is just not to initialize fundamental types, but only the data members of class type. So in other words, we're back to where we started, but just because we didn't do things properly. So for that reason, please avoid writing empty default constructors. It's just not a good idea. It usually is a suspicious sign if you have a just empty default constructor. It might not do the right thing. So let's write a proper one. Let's implement a default constructor that is properly setting all the values to some values. Now, to make a difference, I now set the integer to 42. What else? I use CppCon for the string. Good choice. Yeah, John will be happy. And I'm using null pointer for the pointer since I don't have anything special here. Now, of course, the value is good. We're fine here. However, still I'm not happy because initialize actually is not correct here. This is not initialization. We do assignment. We assign the int, we assign the string, and we assign the pointer. That is definitely something that is suboptimal. Assignment is the operation that you use to change an existing object. What you truly want is initialization, which is a constructor call. That, of course, especially has to do with a string. If you properly want to initialize the string, then we should do it up here. That is what the compiler generates for us. The string is initialized in a so-called member initializer list before we enter the call, the body of the constructor. So the string is initialized to an empty string and then changed by means of an assignment to CppCon. That's, of course, overhead. Yeah, this operation is totally wasted. It's not super expensive, but still, we can do better. So we should definitely move the initializer into the constructor call. We should initialize within the member initializer list. And if this is a good class, then there is a symmetry between assignment and initialization. So if I can assign some value, then I should also be able to pass it as an initializer for a constructor. Now, for the integer and the pointer, it's not super important, not from a performance perspective. But in C++, we indeed consider it to be correct and good style, if not even very good style, to also initialize the pointer and the integer in the member initializer list. And please note the order ISPI. That's exactly the order that I also have down here, because that is the binding order. You cannot change that. You have to initialize these data members in exactly the order that you declare them in the class. All right, and that's great. This is what we should do. This now is a properly implemented default constructor. So please remember the core guideline C47, define and initialize member variables in the order of member declaration. You cannot change it. That is something that is that you just have to do. And please prefer initialization to assignment and constructors. So put as much as possible in the member initializer list. That, as I said before, is considered to be good style, and it's definitely something that will help you also from a performance perspective. It's just the right thing to do. Well, we could now lean back, be very, very happy about ourselves, but code changes. For instance, a coworker of ours might actually decide to add another constructor. It's always the coworkers. Yeah, I know. a coworker might actually decide to add this constructor. And I do hope that based on the discussion that we have already had, you would not accept this code into your code base. You would not allow this to be merged. Why? Well, obviously, because you are not initializing the pointer and the string is default. The compiler would again take care of the string. It's a class type after all, but the pointer would be left uninitialized. So that is a problem. Of course, you explain this to coworker. Your coworker understands this and changes the code to this here. So the string is now initialized to CppCon and the pointer is initialized to null pointer, just as in the previous default constructor. Good. At least the pointer is not initialized anymore. But still, I am not happy about this piece of code. Because now what you definitely see immediately, what catches your eye is duplication. Within the default constructor, in this new constructor, we have CppCon, the initialize, and also the pointer is, the initialization is kind of duplicated. What you should always remember, and that is the takeaway from the first part, make your classes easy to change. In this case, if indeed we change CppCon to some other string, so eventually CppCon is over, we might use meeting C++ or C++ on C. But if you change it in one place and forget it in the other place, you have a problem. And that is exactly what we should avoid, duplication. There's two ways around that problem, two approaches that you could now choose. So the guidelines first. So please avoid duplication to enable you to change everything in one place. The try principle. Don't repeat yourself. And design classes for easy change. So the first option you have is to use a delegating constructor. From within one constructor, now the top one, you can call another constructor. So this line here calls the second constructor, and that second constructor takes care of the entire initialization. In this case, we now provide 42 as our default value, and so all the data members are properly initialized. If you use a delegating constructor, just please always forward to the one that is the most general constructor, usually the one with the most arguments. That is the reasonable thing to do. And also, as a side remark, note that the lifetime of this object starts with the closing brace of the called constructor. So that the object is already alive when we return from this call, which is something that sometimes you might actually exploit. This may be a very, very nice thing in some cases. I don't say this is generally the best thing, but sometimes it's nice to know that. There's a second option though. Guideline first, C51. Use delegating constructors to represent common actions for all constructors of a class. But the second option is perhaps even a little more favorable. We can use so-called in-class initializers. So we can provide the integer, the string, and also the pointer with default values right in the list of declaration. Now, this is how it works. If you mention the I in the member initializer list, then it is initialized as given here. But as for example up here, you do not mention I explicitly in the member initializer list, then the compiler will now use this default and initializes it. And that's also true for fundamental types. So in the default constructor, so up here, I is now initialized to 42. Perfect. In both constructors, the string is initialized to CppCon because I do not explicitly mention it in both constructors. And the pointer in both cases initialized to null pointer. And that, of course, is something that it should be. It should be properly initialized. And therefore, I like these in-class initializers a lot. You simply cannot forget to initialize the pointer anymore. It is virtually impossible. In the worst case, it's always initialized to null pointer. Still, there's one little detail that I would improve. I said before that it is kind of suspicious to have an empty default constructor. In this case, of course, it works. It does the right thing, but it's suspicious. So I definitely would prefer to say equal default. That sets people at ease, and that also shows that you have thought about it. Please, compiler, do generate the default constructor for me. I know it is doing the right thing. It's absolutely correct. That is now, as this little example actually should be. In-class initializers make your life easy, and using the defaults that the compiler generates for you might actually give you a couple of bonus points with your compiler and your friends and coworkers. So C44, prefer default constructors to be simple and non-throwing. Perfect, this is what we now achieved. Then C48, prefer in-class initializers to member initializers, in constructors for constant initializers. And yes, we have constant initializers. We always use the same, so in-class initializers are perfectly suited. And prefer to initialize pointer members to null pointer within class member initializers. My guideline. I just feel this is way too simple to miss. All right. There's a question by Donovan. Some people prefer using parentheses for member list initializer in lieu of using curly braces shown in the example. There is differences, absolutely. Braced initializers give you a couple of extras, like no narrowing conversions, etc., etc. It's probably a little too much to go into detail now. There is differences. And at this point in this talk, I will not give you any recommendation what is better. It's now my choice for this talk to use braces, but in many situations, parens are just as good. Of course, now this could start a heated debate right away. Please look that up, all the details, all the differences. It's quite a list to some extent, and then decide. Okay, and Randy asked, what happens if I initialize in a different order of the declared order? Correct. Then probably it's a compilation error. It should be a warning at least. A compiler should tell you that is not okay. But if you do compile with warnings as errors, then hopefully it is indeed an error. It's not okay. So you should fix this order. All right. Then there is one more thing about constructors that I definitely want to share with you. Something that you should remember. Something that is not just good, but very good. Again, consider widget. And again, consider a constructor that takes an int. Now, this constructor probably does something for real, but in this example, it just prints some output that this constructor has been called. Now, I also add a function called f. That function takes a widget, and that function is called in the main function. However, let's say accidentally, I actually do not pass a widget. I pass an int, which probably was supposed to initialize a widget, but no, it's just an int. What you would expect at this point is that this doesn't compile. You would expect that this code is, giving you the compilation error. Attention, you're using an int instead of a widget. But unfortunately, it does compile. This code compiles and works perfectly. Simply because the compiler wants to be your friend. I know it doesn't feel that way very often. Most of the time, it's a fight with the compiler, but actually the compiler tries to help you. So you use 42, and the compiler reasons about this and tries to make sense of that. So what should I do here? And well, there's only one function f, and the only thing that could possibly work is if this 42 is converted into a widget. Then I could call the function perfectly. And that's exactly what now happens. The compiler converts this integer into widget by means of the given constructor. That constructor takes an int. So by means of that constructor, I can create a widget, a temporary one, pass it to f, and then the function is called. Of course, directly after the function call, the widget is destroyed again. Okay, but well, the call succeeds. Now, perhaps this is something that amazes you, like, whoa, this works, cool. But hopefully it also disturbs you a little bit. It's not great in general. For some cases, this is definitely something that you want to have. But for the general case, I don't think so. So what you should do as a habit is you should put an extra keyword in front of your constructors. Explicit. That little keyword does what it basically is called for. It requires you to explicitly call this constructor. This constructor can no longer be used for implicit conversions. So now the code doesn't compile anymore. The compiler cannot use that constructor, and so there's simply no way to convert an int into widget. So now it's a compilation error, and that's probably good. That's what it should be. Explicit. So explicit is a really, really helpful thing. Absolutely. And this is why core guideline 46 says, by default, declare single argument constructors explicit. Single argument constructors. Generally speaking, you can use this for all constructors, but the ones that take one single argument are the ones that are most easily abused and provide these implicit conversions. And I totally know. I know that you, again, complain. I know that this is not great. Of course, explicit is great, but having to think about this and having to remember to put it on all the single argument constructors, it's a pain. However, this is something that the entire community agrees with. It's one of these wrong defaults. By default, all constructors should be explicit, and we should probably have an implicit keyword or something different, but we have to remember it. So please do remember. It's a very good thing. And you do find a lot of explicit constructors in the standard library, good examples, but you also find a couple of exceptions where implicit conversions are desirable. For instance, C-style string literal can be implicitly converted to a string. We accept that. It's useful. All right. Next, allow me to talk about something different. Something that actually may help you a lot. It depends, as always. But allow me to talk a little bit about the order of data members. I now make a couple of assumptions. The first assumption is that we are now on an x64 architecture. That simply helps me to actually give you concrete numbers. So if you're now using an Intel or AMD CPU, anything x64, then this pretty much applies. If you use any other architecture, the numbers are different, but there will be numbers, of course. In this widget now, I have a bool, I have a float, and I have another bool. The Boolean is 1 byte large on x64. The float, on the other hand, is 4 bytes large. Now I would ask the question, what is the size of this widget? So if I, at this point, ask size of widget, what would that print? And an obvious answer is, of course, 6. 1 plus 4 plus 1, 6. To your surprise, however, this is not the size of that widget. Not at all. This prints 12 on x64. 12, which is twice as large as what you intuitively would expect. So twice as many bytes are taken by this widget. Why? Well, it all has to do with the float. On x64, the float wants to be 4 byte aligned. That's what it wants to be, where it wants to be. That means that the address, the first byte of this float, wants to be at an address that is cleanly divisible by 4. A 4 byte alignment. Of course, now the compiler has to make sure that this is always true, everywhere, in all situations. Even in an entire array of widgets, that always must be true for all the floats in these widgets. So what can I do in order to guarantee that every single widget in my program is properly aligned? I add a couple of padding bytes. Both Booleans are padded by an additional 3 bytes of some type. It's generally invisible, but the bools are suddenly 4 bytes large, at least conceptually. Padding bytes. So in total, the widget now is 12 bytes large. Therefore, it itself is kind of a multiple of 4 large. And the widget itself is now also 4 byte aligned. And with these constraints, it's absolutely certain that all the widgets in the entire program will always be in a place where that the float is properly 4-byte aligned. Now, it's of course unfortunate that it's twice as large as it could be, but imagine that I actually switch from float to double. And if I now give you the additional information that this double is 8-byte aligned, then you can guess that this actually suddenly prints 24. So by just switching from float to double, we suddenly have doubled the size. And yes, the double wants to be 8-byte aligned on x64. 8-byte alignment now triggers padding for both booleans by 7 bytes. 2 times 7, 14 padding bytes, where the real data is actually only 10 bytes. So it's the same mechanism, but again, triggered by this 8-byte alignment. And now is definitely the time when we have to think about that. How can we reduce the size of that widget easily? And I guess some of you have already figured something out. It's actually not difficult. All we need to do is we have to reorder the member data. For instance, we can put the double first, largest first. And magically, these 24 bytes disappear, and the size of widget is only 16. Absolutely fascinating. Of course, once it is in use, you cannot change it anymore. This would change the binary representation, of course. But if you design a class from the beginning, this is something that you probably should pay attention to. In this example now, there's only 6 padding bytes after the second Boolean. The double wants to be 8-byte aligned, starts right at the beginning of the widget. Then directly after is the first bool, and directly after the second bool. And then I just fill this struct by 6 padding bytes. Now, why largest first? Again, experience. My experience is that many people, when they extend a class, add the new data member at the end. Well, it's the new one, goes to the end, naturally. If, of course, you have put the double last, the big things last, then any new data member, even a single byte or another bool, would make this struct larger. So, yeah, 8 bytes larger because of the alignment restrictions again. But if you move the padding to the end, there is at least a small chance that a new data member actually fits into that padding. Now, if you add an int or a float or other bools, the struct doesn't have to get larger. And so moving the padding to the end is actually a nice thing. Then extension is hopefully not too bad. All right. Now, let me take a look at the questions. Okay, there's a few. There is actually a static analysis tool that shows you the order of member data and also the padding bytes. All you need to use is Godbolt. And what you do is you first activate compilation into binary. There's a simple checkbox in the output window, and then you activate the tool pahole. Pahole will then show you, if you also use the class somewhere, will show you the structure. It will show you where the first data member is. It will show you holes and padding. That gives you a pretty nice overview of the proper structure. And of course, depending on for which architecture you compile, that might change. And this is a very nice way to visualize it to some extent. It's not a picture, it's still code, but you get the according comments. All right. Okay, and Frank has a question which I'll tackle a little longer. This looks like something a little bigger. All right. Now, I want to avoid one misunderstanding that, perhaps because I asked the question badly, might come up. So I've now replaced the double by means of a string. And again, there is no standard string in a sense of it always has the same size. So I make an assumption now that I believe Clang is indeed doing in this way. I now assume that the string consumes 24 bytes because it is consisting of 3 pointers, just 3 pointers, 3 times 8, 24 bytes. Now, what is the size of that widget? If your answer is now, of course, 48, no, it's not 48. It's not as bad, 32 only. No, it's not the size of a data member that makes decides on the padding. It's the alignment. It's only the alignment. The string has 3 pointers. The pointers are 8-byte large on x64. 8-byte large usually means 8-byte alignment, so as fundamental types. And so the string is 8-byte aligned. That is what is put onto the widget. The widget itself will be 8-byte aligned. And so these two strings, bools, only need 6 padding bytes, not more. They padded up to 8 bytes, 32 only. So the alignment is the important factor, not the size of data members. So please consider the alignment of data members when adding member data to structure class. And keep it extensible. Leave the padding as much to the end of the class as possible. Okay, and as a reminder, define and initialize member variables in the order of member declaration. This is what I've said before. It applies again. Of course, you cannot simply reorder data members if there's a certain defined and counted on order of initialization. That, of course, is more important. But if you do have freedom, consider to align, to order the data members such that you save data. And of course, the other advantages are obvious. Of course, things are faster and you save memory. It's obviously a big win. All right. Then, so I see Mihal's question. Can we also do, can we use a bit field? Basically, the rules for bit fields are the same. So if you use a single bit instead of a byte, still you need some padding. Absolutely. The compiler will make sure that the padding is available. This is something that you cannot influence yourself. It's the alignment of the surrounding data members. All right. So then let's talk about something else, const correctness, which of course is super important. Const may be the most important keyword in a language, the safety switch in C++. And so I start with a fixed vector again. The fixed vector class is supposed to be a container. I have a type template parameter, that is the type of elements, and I have a capacity. And by the way, note again the name capacity. You now have a full and perfect idea of what I mean. It's the capacity only. I believe we talked about this. Now this container, as all the other containers, has a begin and an end function. That's reasonable. That is expected interface. And of course, this is now used, for instance, in an output operator. I pass a fixed vector, and I traverse all the elements in this fixed vector and print them in some form. Format them nicely such that I'm happy. Of course, you would complain. You would, of course, complain that I passed this fixed vector by value. No, we don't do that. Anything that is bigger than a register size probably should better be passed as a reference to const. So, reference to const. But this little change, surprisingly, makes this code fail. Suddenly, I get a compilation error. And I mean, that the hint is on the slide. It simply doesn't compile anymore because I cannot call begin and end anymore. I now have a const vector. On a constant object, you can only call all those functions that promise not to change the object. Begin and end in this example don't promise that. They're just regular functions. They could theoretically change the object. The fact that they probably don't doesn't matter. I cannot call the functions. So obviously, what I should have is const member functions. And so this const means I will not change the object. But hopefully you've just realized there's so much more about that. Yes, because of this const, now I can call these functions on a constant object. So it's not just this promise, it's actually also part of the semantics of the class. What can I use on a constant object? What is possible? Which operations are available? And as such, of course, this also serves a slightly higher purpose. People suddenly can use the class as expected. Even a constant vector, in a constant vector, I can run over all the elements. So super important semantically, and definitely also from an interface point of view. But, big but, we're not done yet. What I've just added is pretty subversive. These functions now promise, really promise, I will not change the function, the state of this class. But they return a pointer to mutable elements. Not something that you want to have in real life. Sure, the functions, by the way, do their job. They just return a copy of a pointer. They don't change anything. But now subversively, somebody else could change this constant vector. Not good. So obviously, I should also have a const in the return type. Still now, I'm not sure if this is something that you're familiar with. Is this now a const pointer or a const what? Okay, so as a little detour, and since this is CppCon and you will have to deal with this the entire week, so allow me to quickly explain the two different forms of const. I think this is pretty important indeed, especially if you're on site, because then it actually truly matters. So we can put const either here or here. In both cases, however, it refers to type. So the explanation, as John Culp put it in his article, A Foolish Consistency, const modifies what's on its left. So const is a trailing keyword. Unless there's nothing on its left, in which case it modifies what it's on its right. So that is the rule. This is what C++ usually does. Const refers to the left thing. This here is the exception. Const may appear on the left and refer to the right thing, but only if there's nothing on the left. It's an exception though. Okay, so there's two forms of const. And now the initiation, such that you actually survive this week of CppCon, there is now two groups of people that favor both types. The first kind of const is commonly known as West Coast const. The second const, the form of const, the one after type, that is commonly known as East Coast const. And now, indeed, at CppCon, you'll realize that if you're on site, there is two groups that actually wear these little braces and actually find this funny little war that which of these two consts is better. So you will find people that wear this brace, the West Coast const supporters. They wear a yellow brace, of course, on the left arm, West Coast, now on the left. And you will find people that wear a green bracelet, of course, on the right arm. It's East Coast after all, right? Yeah, C++ developers are a funny group indeed. Now, if you're a little worried about this week at CppCon and surviving it properly, here's a little experience from my side. These braces should actually lie around. I put mine up at that bookstore. Now, they were for free. Hopefully that's the same this year. So you pick both up. Now you pick a yellow and a green one, except if you do have a strong opinion, and you put them on the right arm. And then you wear something with long sleeves. Now, if you walk through the aisles at CppCon and you see somebody you want to talk to, but this person expresses strong opinion because this person has only one of these two, you just lift the right sleeve and you found a new friend. Yes, sometimes it's that easy. It's absolutely amazing. this is how you find friends at CppCon. Yeah, just show the right little brace. And yeah, still you're worried that there is just strange people, but no, some people actually wear both. This is a sign of I'm happy with both. Okay, now you are initiated. You know what is happening, but as a last remark, you probably realize there is some comedy to that too. And I believe this was obvious, was made obvious when somebody remarked, and I apologize that I don't remember who it was, that West Coast const actually isn't consistent. It actually should be const West Coast. Now it's consistent. Okay, after this little detour, however, you realize the form that we had right before is the rule. We return a pointer to a const type. Perfect. This is what it should be. These two functions now promise to not change, and they also do not violate the invariants by returning a pointer to mutable things. Now, in the main function, we might create a fixed vector, and we would like to fill all the values with the std_fill algorithm. Unfortunately, again, this code doesn't compile anymore, simply because fill expects iterators through which I can write. These begin and end functions, however, return immutable pointers to immutable elements. So fill doesn't work anymore. So we're not done yet. Actually, we need a little more. Actually, we do not just need these begin and end functions, but we need also the ones that we had in the very beginning. They were not incorrect. It just didn't work for const. So we need both. And yes, you can overload based on this const. I can have one function for constant vectors that returns a pointer to const, and I can have one function for non-constant vectors that does return a pointer to mutable elements. That is what you should do. Now, of course, you have to begin, and it depends what you get based on whether you have a const or non-const vector. For that reason, we also, as a good design, add CBegin and CEnd functions. CBegin will always, and CEnd also will always return a pointer to const elements, always. This is why these two functions are const. I can always use them. They will always produce the same result. Yes, I know. We now have 6 functions that essentially all do the same, but this is just good style in terms of interface design. This is what you should have. This is, at least for containers, this is const correctness. Yes, I know const correctness feels a little bit like a pain, but the win is so much bigger and so hard to actually show that this little code here, this little extra effort is virtually nothing in comparison to the big wins that you have. The interface is clear, everybody uses it correctly. It definitely pays off. So please consider const correctness strongly. But now, of course, it depends on the semantics of your class. It strongly depends. This fixed vector was a value type that actually, if const, should also protect its elements. But of course, there's other types where this is not true. Unique pointer being one of them. So std unique pointer, for instance, has a get function that is const, but it returns a pointer to non-const t. That actually is perfectly okay. This is not a bug. This is exactly as it should be. If the pointer is const, it's not a const on the pointed to thing, the t. So a const pointer still returns, well, a mutable pointer. So if you take a look at the main function, a const unique pointer to int, this is just a mutable int. Just as this pointer is, this is a constant pointer, but it's not a constant int. We can change the int. If you want to make the t const, then you have to say so. You have to add a const either at this point, so make the pointed to thing const, or at this point. So these two are semantically equivalent. And so, yes, the unique pointer does the right thing. It depends on its semantics. So, Corklet and con2, by default, make member functions const. That is an omission that I unfortunately see too often. So please, if you do write a class, make sure that member functions are const. Now, so by default, make them const. And of course, there's some that are not, but every member functions that should be const by default. And again, it's one of these defaults that are wrong. In lambdas, we now finally do the right thing. But again, we have to remember that const is so valuable and we have to put it explicitly. All right, and const correctness is part of the semantics of your class. Definitely, please don't forget. Const, by the way, is so important that this year we'll have another const talk. So Rainer Grimm will talk on Tuesday about const and const expert. 1 hour about const and the according other things. So const is important, so please check that out too. All right, however, let's talk about encapsulating design decisions. Because no, I'm not entirely happy about the code we just fixed yet. Now we do have const correct behavior, that is great, but actually we should do more, much more. I'm not happy about the return type. And of course, it's about changing things again. Right now, you might not suspect it, you might not expect it, but eventually you might actually change this piece of code. For instance, some coworker might tell you that it shouldn't be a pointer anymore, you should return a class type. A class type gives people the opportunity to actually introduce some debug information. So you want to change to class type. However, as soon as you do that, the calling code, so people that use that might actually have a problem. Because you, for all time, you promise to return a pointer, and they might use that. Your interface returns a pointer. They might use a pointer directly, not auto or something else. So this code might not be changeable later. That is a problem. You always want to keep your class easy to change and to extend. What we do here, for very good reasons, is to provide a couple of type aliases. So std_vector does it, list does it, all containers do it. Your container, if you have something similar, should do it too. And please do not just believe it's just for containers. If you do have things that might change later, please provide some kind of encapsulation, some kind of abstraction if necessary. Iterator and const iterator help. So the return types should be changed to these iterator types. Nobody needs to know that you're returning pointer at this point. Nobody. And this leaves you much, much more freedom to change things later. By encapsulating this detail and not showing that it's pointers, you actually give people a cleaner interface. It's nicer, they don't have to know about these details, and you can change your code much, much more easily. By the way, again, it depends. Not every single design decision needs to be encapsulated. std_vector, for instance, has a function called data. That function is expected to return a pointer or pointer to const, depending on which data function we're looking at. This function is supposed to return a pointer. So in this case, it should not be encapsulated away. That shouldn't change. It's a very specific semantic. Okay, but begin and end definitely should return iterators, not pointers. So please encapsulate design decisions, things that might change. And by that, of course, design classes for easy change later. And yes, of course, it's hard to remember what is, to estimate, I should say, what will change in the future. Any kind of prediction is hard, especially if it is about the future. Therefore, it's always a good thing to perhaps encapsulate things a little up front to do not have problems later. All right. Now, because we're talking about, did talk about const and we talked about member data, there is perhaps one more detail that I would like to add. We might, of course, also have const data members or reference data members. Still, these two kind of pose a problem, a pretty unfortunate problem, because if you do have any const data member, Or if you do have any reference in your class, then the compiler would not generate the assignment operators anymore. And of course, I'm talking about copy assignment and move assignment. These two simply do not work anymore. I believe with the const, it's most obvious. I cannot write to a const thing anymore. I cannot change it. That's the point of const. So what should the compiler generate? It just doesn't know. With a reference, it's a little less obvious, but reference is a fundamental type. So in the default case, you would not write through the reference to some other double. You would actually change the reference, which is something that you cannot do. And again, the compiler says, no, it's not clear to me what you want. I will not just generate it. The copy assignment operator would be implicitly deleted. So it is as if you have written equal delete, and the move assignment operator is just not declared. You don't have a move if you use any of these two data members. So simple piece of advice, you should not have const data members. Data members should probably be private anyway. And of course, this does not apply to static const. That is okay. This is not copied as part of a widget itself. This is different. But a const data member is actually not really advisable. And a reference could actually be rewritten in the following form. Instead of a reference, you store a pointer. You make it private, and you pretend that you store a reference. So you pretend by taking a reference and by returning references, for instance, but you do store a pointer. That is copyable and does not pose any problem for assignment operations. Alternatively, if you don't want to code this yourself, there is in the function header a stood reference wrapper, which does exactly that. So this is represents a reference to double, but it in itself, it stores a pointer and therefore is changeable. So that is definitely a nice alternative. So don't make data members const or references. This is what C12 tells you. And remember that a class with const or reference data members cannot be copy or move assigned by default. You would have to implement these functions yourself. And of course, again, you would have potentially problems with a const member. It just is not great. And generally strive for symmetry between the two copy operations and also strive for symmetry between the two move operations. This is what people expect. Your class would be highly surprising if there is an asymmetry. If I can copy construct, but not copy assign. It indeed would be surprising. Nobody likes that. All right, and there's just one thing left, which is actually not really about designing classes, but some detail that I found many people to be confused about, or surprised about, I should say, even in classes where I expect people to have a very good level already. So let me just add this as a little bonus, as a little clarification, for instance. Again, I have a widget, and this widget has two functions that are called do something. The first do something function is in the public part of the class. It takes an int. That's what I call function 1. And I have another do something function in the private section of the class. That one takes a double, and I call this function 2. At some point, probably in the main function, I create a widget, and I say do something, and I pass a 1.0. Now think about this for a couple of seconds. Which of these two functions is called? Function 1, the public one, or function 2, the private one? Now, at least 80%, sometimes 90% of students in my classes usually vote for function 1. It's obvious. It must be function 1. That's the only function that's public. And of course, it's unfortunate because if I pass a 1.0, then that one needs to be converted into an int. But okay, it's a 1.0, not a 1.1. We don't lose anything. However, surprisingly, it's not function 1. It's actually function 2. But no, it's not calling the function. This results in a compilation error. what you do get is a so-called access violation. The compiler tells us that function 2 is not accessible. It's a private member function, so it doesn't work. Very surprising indeed. Very surprising for many people because it's the private section after all. Yes, it's private, but private is not a visibility label. It's an access label. So the compiler actually first takes a look at the entire class and finds two functions called doSomething. Then these two functions are passed over to the overload resolution. The overload resolution would say, given 1.0, I would choose function 2. And then only in a later step, we discover, oh, it's actually private. We cannot call it. And no, there's no going back and the overload resolution doesn't change its mind. No. Function 2 selected, function 2 it is. If there's a compilation error later, it's a compilation error. In other words, the private label does not really hide things. It just restricts access. Everything inside a class is visible. Everything. The private part, the protected part, despite the fact that all of these words sound like full encapsulation. No, there is no full encapsulation. Everything is visible. Whatever you do in the private section, everybody sees that. And so please consider classes as class objects. Yeah, so basically imagine that you have a class widget, which actually would make for a great keyword. But no, it's not a keyword, but this is what you should imagine. Everything is visible by default. And so it does matter what you do in the private section or as a protected section of your class. It may play a role in the overload resolution. Perhaps surprisingly, but this is how C++ works. Perhaps you ask why. Okay, I can add this in 1 minute. Björn himself, to my best knowledge, actually realized that it might be surprising if calls to one function, like this doSomething with a 1.0 from different positions in the code, resolve into different functions. So it should not make any difference whether I call this function from outside or from within the class. It should always, under all circumstances, resolve to the same function. Therefore, this label here is checked very, very late in the call resolution. So in other words, name lookup first, then overload resolution, and then only after that, I actually check the access levels. Very, very late indeed. And perhaps C++ is a little special in this context. All right. Now, that's all I have. The time is already up, but allow me to summarize. The most important pieces of takeaway. Separate concerns. It always helps. It's one of the most important pieces of information that you can get. It really helps. Please restrict the urge to put everything into one class. There should be many classes. Separate concerns, tested separately, implemented separately, changeable. So design classes for easy change and design classes for easy extensions. And last but not least, the topic I unfortunately didn't go into too much detail, but still super important, design classes to be testable. Ultimately, that may be the check if a class is good. Good code is testable, else it's not. All right, then thank you much for your attention. Now I'm going to try to answer perhaps a few more questions in the remaining time. Okay. I have a question from Vyacheslav, who says, or asks, cons members make a class non-copyable, but it's still movable, right? Okay, it is move constructable, but also not really movable. If in the thing that is supposed to be moved, you have a const member, of course, this const thing cannot be moved. You would fall back to copy. So the move constructor is kind of incomplete. The copy constructor would take over. So it's movable in this sense of you can try to call it, but the copy operation would be called instead. Move assignment, however, is indeed disabled. There is no move assignment because you cannot change the thing, neither by move nor by copy. Once assigned, the const is fixed. So no real move. Not even move construction, unfortunately. All right. Then some anonymous attendee asks, if you define type const pointer begin const no except, do you need to define type const pointer cbegin const? Okay, why not just define cbegin? This is to do, of course, with the interface. If you call begin, you basically now get the version that corresponds to your current status. If you're const, you get a const iterator. If you are not const, you get a mutable iterator, or iterator to mutable, I should say. cbegin will always answer the question in the same way. You will always get a const iterator. So it is actually nice to have two functions, begin, that depending on the state, do the right thing. If you would get rid of one of the begin and replace it with cbegin, you would have to change the call site again. So it actually makes sense to have all six. It's a good style still. But okay, again, it might depend on what you have in mind. Okay, George asks, obviously this is a big topic, so don't expect a big, super detailed answer, but can you provide an example of a big win in the context of const correctness? First of all, const is something that helps you. It helps you to not modify something accidentally. Big win. Accidents are far more rare. It also helps callers of your code to know what actually works and what not. So it's like a documentation in the class. And after all, const is a security switch. It will always work in your favor. Security is something that you should not lose lightly. Absolutely not. Okay, I know this was a very short answer, but I'm now available in Gather Town. So it takes me a minute or two to go there, kind of physically, but I hope I can address a couple more questions. Okay, else, thank you very much for attending and have a great rest of the conference.